Hi, welcome back. And this time we're in internal flows. And this is actually starting to get near and dear to my heart. My PhD was in doing some seriously heavy computations in internal pipe flow that was turbulent. And so I'll show you some videos here at the end of just some turbulent flows and show you why. I found it pretty fascinating. And just as time as computers were really starting to ramp up and really give you that insight. But internal flows, laminar flow within internal flow, so not turbulent, laminar, and we'll talk about what that means. There's only so many flow fields we can actually analytically solve. Now, when we come back into the graduate fluid mechanics book, we will kind of highlight on a couple other ones that are interesting where we can get sort of some analytical insight. But internal flows, really, we're talking about, so for this first example, we'll talk about flow between two parallel plates. And so the flow, that's supposed to be a parabola. So the flow ends up, being sort of fastest in the middle and then kind of slows down towards the end. Why? Because of viscosity. And you have what we normally would do when we're drawing these diagrams is do these sort of dashed lines to highlight that that's a wall. And so you have the velocity, and I'm going to choose this to be the x direction. Okay. And so I'll just put my coordinates here. That's x and that's y. I don't remember if I actually have them sitting on the wall or not. We'll see. I may have to drop that down to the floor. But so basically, your boundary conditions are that velocity in the y direction is 0. It's nowhere happening. That's not a boundary condition. That's just sort of an assumption. And that you would have your boundary condition. Actually, I think I'm going to have this at 0, so that your boundary condition at y equals 0 and at y equals h is equal to 0. Okay? And so then when you go through and you look at the momentum equation, so let's write it up here. Time rate of change of, actually we'll just do the x direction, okay? And then I'll write out, actually I'll write out the two-dimensional version of this so you can really see it. I usually do the complex form. So rho u du dx plus rho v du dy, and that's equal to the pressure gradient in the x direction and viscosity times we'll do the full expansion. Second with respect to x, second with respect to y, and just 2d. So that's good enough of the x velocity. Okay, so which things go to 0? So, well, this term v is 0, so that's going to 0. X is not actually varying in the x direction, so we would call this fully developed flow. This is a really long channel, and so there is no variation of x in the x direction in the flow direction because these are like infinite plates, if you will. Okay. Likewise, the change of velocity is not changing with respect to time. We're sort of imposing here, this is laminar, so it's not changing. And then over here, you have, again, no changes of the velocity field in the x direction, and so you're only left with the change in the y direction. So this whole thing gets really easy to integrate. It's basically this whole left-hand side became 0, and there's only one term, and it was the second derivative. And so you can integrate it. And so I'll do the integration. So you would have some constant of integration, and then 1 over mu dp dx times y is equal to du dy. Why? Basically, we will solve this problem assuming that the pressure gradient is constant. Whatever this pressure drop in the x direction is constant. So it's constant, so I've moved it over the other side, I've dropped the mu to the other side, and so it is constant integrate. That's what I pick up with y, and then some unknown term, cy, c1. Okay, and so then when you integrate again, you would get another term, c2. The c1 integrates to a y in there, and then integrating this, you get a y squared over 2. And so there's the term 1 over mu dp dx and y squared over 2, and that's equal to u. And so you have two unknowns, and you have two boundary conditions. I've got basically the velocity has to be 0 when y is equal to 0 and when y is equal to h. And so you do the math, and it looks like, I'll just write it down and I'll figure out where my coordinate system actually is. 1 over mu dp dx, and this is y squared over 2 minus hy over 2. So I think that's right. So when y is 0, I'm going to say 0, 0, yep, it's gone. And then when y is h, this gives me an h squared over 2, and then I get a h times an h over 2, and so it wipes out. Yep, there we go. So that's it. It is quadratic, so this is a parabola, and that's laminar flow. And so what's interesting about this in a channel, we'll see there is a chapter in Panton that actually gets into some advanced turbulence, and so we will eventually kind of come back to this. And so what's really cool about flow between two plates is mathematically I can actually come in here with a tickle. And I can leave more of these terms same and sort of insert a tickle. I have to make sure that tickle is conserves mass, so that it's the right kind of tickle between x and y. And then you can actually solve for an infinitesimal tickle. And so what you end up doing is saying any terms that pick up an infinitesimal squared is peanuts. And you actually can solve and show that within two plates there is a Reynolds number, right back to our last lecture. There is a relationship between the flow and viscosity and the density that is unstable. And so there's lots of interesting research that goes along into this sort of transition from smooth laminar to turbulent flow, where it's all this mixing and crazy stuff going on. Now, if this is the first time you've heard turbulence, usually you'll hear it in an aircraft, it's called turbulent. Well, there's turbulence all over an aircraft. When the aircraft means there's turbulence is there's a large scale sort of atmospheric eddy or turbulent eddy in the atmosphere that's going to go womp and kind of, have the plane sort of bounce a little bit. We're always developing turbulence along the edge of the vehicle, usually on an aircraft. A couple people try to make fully laminar aircraft, but it's pretty hard. Okay, so that's kind of channel flow, and you can repeat this in a pipe. So you can come back in here and do it as a pipe with diameter d, if you will. You'd have to start with the polar cylindrical coordinates, and you still end up getting a parabola. But what you can do with the pipe, where this becomes a little bit more interesting, is you can actually solve for the flow rate, q. So you would integrate that velocity profile, and you would get pi times the way they usually handle it is the pressure drop over L. You pick up a 128 and a mu, and then d to the fourth. So from a laminar flow rate, your flow rate actually goes like the diameter to the fourth power. So interesting. A lot of times you can think through what might be happening in like your sprinkler system and things like that. You'd have to calculate the Reynolds number to make sure you're not turbulent, but a lot of times you can really increase your flow rate by just doing a slightly bigger system. Okay. Now, in flow between two channels, there's this very specific number that you would transition to turbulent. What they usually just leave in the undergraduate world in a pipe flow is the rule of thumb, and I'll put it in green. The rule of thumb is that somewhere around Reynolds number 2300 is where you would start to transition to turbulence. It's just a rule of thumb. So one of the cool things about the pipe flow, so in the you sort of flow between two parallel plates, you can actually solve for a tickle, and then there's a certain critical Reynolds number. So below it, the tickle decays exponentially, and above that critical number, the tickle grows. You don't have that in polar cylindrical coordinates when you solve this thing. It's actually stable to infinitesimal disturbances. And so in fact, there's some really cool experiments that have been done along the world where if you really isolate a pipe and keep all the vibrations and turn off the fans and all that, there's some people that have gotten some really cool visualizations of laminar flow at a really high Reynolds number, and then you flick the pipe and boom, it goes turbulent. So pretty cool stuff. So that's why this is sort of just a rule of thumb. You know, you got to make sure, especially if you're thinking about like a pipe that might have all sorts of either gunk in it or roughness. You know, don't just get stuck on this. But my Reynolds number is lower than 2300. It should be laminar. You know, just remember it's sort of only a rule of thumb in pipes. Okay. And so I thought I would just kind of finish with some cool videos of that transition to turbulence. And so got here, this is a nice YouTube video. I'll hit play and sort of get out of the way so you can see it. But, you know, very simple system. And they have a die, a blue die that goes in, that's kind of running. And it's got the Reynolds number on the bottom. And so as you increase it, you can see you actually start getting these like waves, disturbances, and then as you go up, this really starts getting more violent, and then you actually get it to start corkscrewing, so it enters actually sort of a third dimensional, and then now it's really starting to sort of twist and break up and get a whole bunch of eddies going, and then pretty here quickly you just see mixing, and so there's all sorts of stuff now going on with turbulence and visualizations and things like that. So anyways, it's a pretty rich field of turbulence research. You know, the fully understanding turbulent flows. This is I'm just going to leave with this and saying this is actually one of the hardest parts. I will come back and talk more about turbulence in the lectures, but I'll just leave you saying, you know, predicting the effects of turbulence is what you have to do to predict drag. And so think of any system you may be looking to build, whether it's a car or an airplane or just whatever it happens to be, you know, doing that estimate, which we would call, you know, computational fluid dynamics if you're using a computer, is really challenging and not easy to do. And so you will find yourself in almost everything you do, even though computers are getting better, you're going to have this balance between experiments and computations. We're not in a world that computers can actually completely nail it. And I'll spend some good time really describing why and what are the challenges behind computational fluids. And so turbulence and its nature and how is it self-sustaining and what are the structures and what are different things, different pressure gradients due to the structures. We'll actually cover some of that, especially as we sort of go from this chapter, which is just the internal flow version of this, to external flows in boundary layers and things like that. We'll see some of it here in the next few lectures. But this is what makes fluid mechanics ultimately really challenging, right? And so, you know, some of the easy stuff in fluid mechanics, whether you're just calculating pressure drops through a pipe and sort of friction factor, like some of the stuff we've been doing, Bernoulli, yes, it can be sort of easy to estimate, but then fluid mechanics quickly has this turn towards like, and now it's really hard to estimate. And so a lot of work has to be then done, like I said, with experiments, with computational flows, and then just that's why it's powerful to have this math. That's why I'm teaching this course on the way I am, to sort of make sure you're leveling up your math, because there are some pieces like this that if your math is powerful enough, we can get you some more intuition in terms of flows that we can solve. Like this is basically the end in undergraduate class of the flow that you could solve analytically, and it's kind of boring. It's just a parabola. And so in the, you know, in Panton's book, in the graduate book, we'll actually come back through and give you some more examples of things you can solve analytically. That is, it's actually very helpful for you to start understanding the intuition, because it's much easier to get intuition from equations, simple equations that you can plot, before you're sort of forced to be just, you know, throw it in a computer or throw it in a wind tunnel. So, anyways, I'll get off my soapbox. This is a passion of mine. That's why I love thermodynamics, fluid mechanics, and ultimately trying to make things go fast. So we'll see you next time on the book club. Thanks.